they will catch us. So the recording also started. So today we start our last day of Azarquiel school with some cosmology. And Mar Azarquiel will be our lecturer this morning. Thank you for joining us, Mar.
Okay, so
you can share your screen now.
Yeah.
Okay, let's start.
Can you see the screen, the presentation?
Yes, we can.
Okay, thank you. So first of all, just to thanks all the organizers for the kind invitation. I mean, it's a pleasure just to participate in this school. Indeed, I did it when it was there in Istanbul some years ago, and I must say that I have a great time there with all of you. So I will talk today about the early universe, cosmology, but then before Big Bang and nucleosynthesis. So I want to talk a bit about how we describe the evolution of our universe on average. So we live in a expanding universe, and what the observations tell us about this universe. They mainly focus on the cosmic microwave background observations. So this is just the main theme for this lecture. So how to explain what we see in the cosmic microwave background radiation, and then why we need a period of inflation previous to Big Bang nucleosynthesis to be able to explain those observations, the consequences of this, and how we model this period of inflation, and what we call slow roll inflation, and a bit of modeling and things like that. And today, what we can get beyond the CMB observations from inflation, and I would talk at the end just describing about primordial gravity waves and primordial black holes. Also, these are today just the main focus of activity in the field of inflationary physics, and there are some interesting results. So just a bit of the bibliography. There are many good reviews on inflation and cosmology, mainly from different summer schools, like the tacit lectures on inflation. So here are a couple of them that I like, and then I will also recommend just to check in the web pages from the main satellites for the CMB previous to Planck, to the latest observation WMAP, and then also the Planck web page, and about gravity waves. So the LIGO page, that they really had done a great job. So we start. So we live in an expanding universe, and also our universe is homogeneous and isotropic on very large scales. And today, that was what it was called the cosmological principle, just to develop the first models of cosmology, of early universe cosmology. And today, from observation, we know that, okay, for the distances more or less larger than 100 megaparsec, indeed, our universe looks homogeneous and isotropic. And also, this is what we had seen in the first detection of the cosmic microwave background radiation done in 1965, 1967 by Penzias and Wilson. This is what they saw. They saw just an homogeneous background, sound radiation in the microwave range that was coming from everywhere. They couldn't identify the source. So it has a cosmological origin. We know this is just a picture of our universe when it has just 300,000 when it was 300,000 years old. But we know that it cannot be that homogeneous and isotropic because today we see this the structure. So we need also just the small fluctuation on the temperature of this background just to explain the origin of the structure. And that was detected years later by, first of all, by the Kobe satellite in 92. And we know that this fluctuation of the order of 10 to the minus 5 is a small number, but we need to explain that number. So this is going to be one of the problems of the standard cosmological model. So our expanding universe, homogeneous and isotropic, how we study the evolution just with the Einstein equations, are just the equations that describe the gravitational interactions. So in this side of the equation is just the geometry of our space-time. And on the other side, we have to put the source of our gravitational interaction and how the space-time will evolve and how the space-time is curved. So what we do is an ansatz. And now we just model the space-time, the metric of the space-time with the Freeman-Robertson-Walker metric, homogeneous, anisotropic. So we just take spherical symmetric for the metric for the spatial session, just modulated by some time-dependent function that is what we call the scale factor. So this scale factor, the variation of this scale factor is what is going to give us just the rate of expansion of our universe. That is what we call the Hubble parameter. So the Hubble parameter is what it was observed by the Hubble in 1929 in his famous Hubble law. So what he observed was just the expansion of the universe, what we have interpreted, like the expansion of the universe, that the galaxies on average were receding from each other. And the relation between the velocity and the distance, it was, that is what is called today the Hubble parameter. Just to get this rate of expansion, we need to just fill our universe with something, with matter and energy. And we model that when we just describe the evolution of our universe on average, we model that we just with what we call a perfect fluid, and we characterize this fluid with some energy density and the pressure. And the relation between the pressure and the energy density is what is called the equation of state. Once we input this metric, the Freeman-Robertson-Walker metric, in our Einstein equation, then we get the dynamical equation for our universe. First of all, the rate of expansion, the Hubble parameter, that depends on the energy density and also on the curvature or the spatial session, and then the second derivative of the scale factor that gives us the dynamic of our universe, how the rate of expansion is changing. And then we also get the energy conservation for our fluid, how the energy density is varying depending on the expansion of our universe. Depending on how we model this, if we have just a fluid that is made of massive particles, the energy density just is diluted due to the increase in the volume of our universe, that is due to the increase in the scale factor. If we have filled our universe with radiation, just the energy density just falls like the scale factor to the fourth. And then there is the other component that is called a cosmological constant, that it doesn't, the energy density doesn't vary with time, and it remains constant. From that, we can today, we know that our universe is filled with a mixture of matter and dark energy in general, what we call, or something that resembles too much to a cosmological constant. The radiation is subdominant today, but if we go backwards in time, what we get is to a period where instead of matter dominating the expansion rate of the universe, radiation starts dominating the expansion rate of the universe. And during that period is when the first nuclei were formed, and then from that onwards, atoms and the structure and galaxies and so on and so forth, that I'm not going to describe. So whatever physics I'm going to try to describe, it will be before Big Bang nucleosynthesis. This is just the standard cosmological thermal history of our universe that we know very well and we can describe very well. and it has been checked from the observations. But about the future, so it depends really what is this component that we know that is there, that is behave like a cosmological constant today. And what is doing is that the rate of expansion today, instead of being decelerated, is accelerating. So our the scale factor, sorry, the scale factor, the second derivative is positive instead of being negative. This is one of the question marks. I mean, we really don't know what is this component that is driving the expansion of the universe and is making that is accelerating today instead of being decelerating. This is happening just more or less today in cosmological scales, not in the past. But we don't know. I mean, not during Big Bang nucleosynthesis that the rate of expansion was controlled just by the fluid made of relativistic particles, so radiation. But we don't know before Big Bang nucleosynthesis. So it may happen that the expansion of the universe was again accelerated, and indeed, this is what we think that was happening. Why? So this picture is, some relations that will be important later. So we live in an expanding universe. All the physics is encoded here in the dynamic of this scale factor. And this is what controls how the distances, how the lengths behave in the expanding universe. So all the physical distances just grows with the scale factor, and the comoving distances, what we call the comoving distances, are those that are not being affected by the scale factor. All the wavelength of all our perturbation also grow with the scale factor, and physical momentum just decreases. It's just the inverse of the wavelength, so just decreases the physical momentum with the scale factor. So comparing different wavelengths, we define what is called the redshift. And this is just give us an oscillator of the distance at which the source is, and also of time, because everything is changing, time and distances. So the inverse of the Hubble parameter gives us what is called just the typical side of what we can observe. I mean, we receive information through the light that arrive from the different sources, and the light that just propagate at a constant speed. So there is at each time in the evolution of the universe, there is a typical distance from which we can get information, and this is the size of the observable universe. Whatever is the size of the real universe, we don't know. I mean, but what we had to compute at each time is what is the size of the observable universe. If we divide it by the scale factor as usual, then we get what is called the comoving horizon. And what is important is just the causal horizon, the maximum distance that each time the light can travel. And this is important because the causal horizon must be inside of the observable universe. Otherwise, we cannot, we were seeing patches that are not causally connected with each other. So this is just the distances that at each time we need to compare with each other. So just the famous picture of our expanding universe based on what we know from all the observation, astrophysical and cosmological. So we live here. This is just the cartoon made by this collaboration. WMAP is a nice cartoon, and we all use it since years ago in all the presentations. So we live to here. The age of our universe is more or less 13.7 gigayears. And as the universe expands, the temperature of the universe just decreases. So today is a very cold place, but in the past it was very hot. At some point after the Big Bang, and we don't describe exactly the t equals 0 point, we don't know what is happening just exactly at the origin still. This is a big question mark, but a bit later on, the universe started expanding, nuclei just form. And after that, just the atoms, the universe became neutral, and just photons start propagating freely because they cannot find any other electric charges to interact with. And this is the origin of the cosmic microwave background radiation. Microwave because today we detect that radiation in the microwave range. At the time of formation, the universe was very hot and the temperature was roughly of 3000 kelvins. This is what we detect today, that it gives us a lot of information about the evolution of our universe. There is some dark ages that we don't see anything. There are just other satellites that are trying in the future trying to extract information from that epoch, and then the structure start forming. Here is another picture, typical picture of the evolution of our universe, just with some energy scale and just information. At the end of the day, our universe is made of particles, and the theory that describes all these particles and the interaction of all these particles is just the standard model of that we have been checking in the accelerators, and in particular in the LHC at Geneva. But then from that we know that, okay, previous to the Big Bang nucleosynthesis, we have the quark-anion transition and the electroweak transition. Before that, our theory of particle physics ends. And then this is just an arena for speculation and just for introducing beyond the standard physics. There are many questions that we need to answer in cosmology and also in particle physics. So we need some extension of the standard model of particle physics, the same that we need some extension of the standard cosmological model. Problems. So what we observe today, what then the data from the cosmic microwave background radiation is telling us, is that we live in a spatially flat universe. And this is a problem. Well, it's a problem because to get that, we really need to fine tune the initial conditions to start the evolution of our universe. And we don't like that, just fine-tuning things and just adjusting too much whatever parameter we have in our model. We don't like that. So we prefer just to look for some dynamical explanation of how we had ended in really a spatially flat universe. Then, as I say, what we describe on average and what we saw in the CMB is just a universe and that on large scale is homogeneous and isotropic. And this is also a problem. This is what is called the horizon problem, because as mentioned before, at each time we need to compare on the side of our observable universe with the side of the causal horizon. And what we discovered is that today, all those photons coming from different directions and regions were not in causal contact in the past. But what we observe today is just that on average, they are really at the same temperature. So why? If they were not in causal contact, why they had ended at the same temperature with just a tiny fluctuation on top of that? And that the origin of those fluctuations that we really need to be there just to explain how the structure will form later on. And well, whatever, because we need to extend our model of particle physics and cosmology. So we tend to produce many other stuff when studying these extensions that we don't see today. So at some point we need to get rid of all these, what is called relic that can be monopoles or topological defects that are formed during phase transition and so on and so forth. So this really depends on our theoretical model, but typically it's also a problem that is there. The flatness problem. So if we compute, just we have our Friedman equations, and this gave us just the rate of expansion at each time, each epoch during the evolution of our universe, and we can just normalize the energy density controlling this rate of expansion by what is called the critical energy density. That is the amount, the exact amount that we will need just to make the universe flat. So, and here is, we define the density parameter, always just normalizing the energy density with this critical energy density. So the evolution of this density parameter, the one that is made of all the components of the energy matter content of our universe, is such that is rather unstable. So if we are at some point slightly above the critical energy, this will evolve and will increase this difference in time. And if we are slightly below this critical energy, then we will depart more and more just from this flatness value. So this is, we don't like these kind of things. I mean, really, we will need to tune this parameter at the time of the Big Bang nucleosynthesis, just for the universe and just to be also spatially flat to an accuracy of 16 orders of magnitude. So the solution is that we get this evolution only when we include matter and radiation in our universe, only when we include something with an equation of a state that is positive. And this gave just some decelerated expansion. So whenever we have decelerated expansion, if we have decelerated expansion always since the origin of our universe, it is very difficult just to explain why we had ended in a flat universe today. The solution is just including some period that just reverse this tendency. So some period where the expansion is accelerated instead of decelerating. So during that period, so what happened is that even if we are departing from above or from below, we will converge to one and we will end in a flat universe. This is just pictorially what is happening is that, okay, it doesn't matter. We don't know. We don't know if it was just close or open our universe. But again, what we can just observe from our universe is just some region. So if we just include a period of accelerated expansion, what happened is that the whole universe expands suddenly very fast, and our observable universe will look flat. And this is what we need just to explain the observations. So because this scale factor is just suddenly increasing almost exponentially, we get rid of this term, and this term is irrelevant today. We don't know if it was relevant or not in the past, but today the universe looks flat. The horizon problem is just is very important also, and it's just comparing that the side of our observable universe given by the inverse of the Hubble parameter with the causal horizon, the distance, sorry, the maximum distance that the light can travel between two times. And this causal horizon, again, if we are including only matter or radiation, something with an equation of the state that is positive, so that the universe is decelerating, then what happened is that this causal horizon in the past was larger than the observable side of the universe. So the photons that we see arriving from everywhere today were not in causal contact in the past. So why are they at the same temperature? That's the question. We can also represent it here. So here is just the causal horizon. And now this is today. So we draw the latter ray trajectory towards the path. And at the time of the formation of the CMB recombination, so we see that the 2 points in the past were not in causal contact. And today we see then at the same temperature. The solution is just the same that to explain the flatness problem. This is what we get if we only consider that the universe has been decelerating always. So the solution is just to include previous to the formation of the CMB a period of accelerated expansion. So we just increase our causal the history of the universe, and we now these 2 points that we observe today in the CMB have time enough in the past just to be in causal contact. So this accelerated period of expansion just solve also the horizon problem for us. This is what we call inflation. Some period of accelerated expansion previous to Big Bang nucleosynthesis. Still, I mean, we don't know exactly when, but it must end. What we know is that it must end before Big Bang nucleosynthesis, because the nuclei must form when the universe was dominated by radiation, but above of relativistic particles. So we just assume that we have, and we try to model this inflationary epoch where the universe suddenly expand, just the scale factor will grow almost exponentially, and this will make our universe to look flat afterwards, and also will make that, okay, previously the photons that we will observe in the CMB were just inside the observable universe at the time. This sudden expansion just takes those regions outside the observable universe at the time, and then when the inflation ends, will just take then again inside the observable universe. So the important thing is that what we observe today at some point was in causal contact. And this is what inflation will make. Will just take the fluctuation that were inside, and then just the wavelength suddenly will grow exponentially. Remember that all the physical distance just goes with the scale factor. The scale factor grows exponentially. So all this fluctuation will go outside the observable universe at the time, and then later on when inflation ends, they will just enter again in our universe. So this is the gain of inflation with the fluctuations. How we model this period? So it's not very difficult, because the only thing that we had to do, in a sense, is just to play with the scalar fields. In particle physics, every time that we need to model something, we like to play with the scalar fields that are Lorentz invariant. So because of that. So when we have some scalar field with a potential that is dictated by the kind of interaction that we have, and some kinetic energy due to the motion of this field along this potential, we can enter in the regime where the kinetic energy is really negligible. So we enter in the regime that on average, this scalar field is behaving like a cosmological constant, something with a equation of a state that is negative and almost -1. And the way just to get that, just to stop the field so that the kinetic energy is negligible, is just provided by the own expansion of the universe. So the motion of this scalar field along this potential is like the motion of a damp harmonic oscillator. So when the friction given by the rate of expansion is large enough, we are in the overdamp regime, and the field is practically stopped in just some region of the potential. So this is the way that we get inflation. To characterize that period, and almost with any potential, we can get a period of inflation. Another thing is that we can get enough inflation just to solve the problems, but the only thing that we need to do is just to identify in which region of the potential we can just fulfill those conditions, that the kinetic energy density is subdominant. And typically this is what is called a slow roll inflation, and we characterize that with just some slow roll parameters. That is just comparing. For the eta parameter is just the curvature of the potential with respect to the height of the potential, and for the epsilon parameter is just the slope of the potential with respect to the height of the potential. When these parameters are smaller than 1, then we can inflate. And all the prediction of the inflationary models are given just in terms of these slow roll parameters. In a slow roll inflation is not that difficult, just to get the basic prediction of our model. The important thing is, as I said again, what this period of accelerated expansion is doing to the fluctuations. So we have a scalar field that is dominating the total energy density of the universe, just controlling also the rate of expansion. And if it is a quantum field, it will have a quantum fluctuation that will become classical. So the fluctuations are there. The wavelength of those fluctuations, just due to this almost exponential expansion, will grow, will go out the observable universe, and then later on they will re-enter in our universe, and they will provide the initial condition for the generation of the CMB. And we can compute very easily during inflation what is the spectrum of this fluctuation. This is the nice thing. And once we compute the spectrum of this fluctuation during the inflation, once they go outside the universe, this amplitude remains practically constant. And then this is what provides the initial condition just to follow later on the evolution of our photons and the evolution of the fluctuation in the temperature, and just to get the spectrum that we observe in the CMB. So the receiver for inflation is just for cooking a model of inflation is just choose your potential, your preferred potential, and okay, it depends on your preference in particle physics and if there is another problem that you want to solve. So the motivation for the inflationary potential comes most of the time from particle physics, or at least they did come in the past from particle physics. And just get your prediction, your slow roll parameters, check that you have enough inflation to explain the horizon problem and the flatness problem that is of the order of 50, 60 if-folds. Just check the amplitude of the primordial. What you generate during inflation is always called primordial spectrum, and just set the value of one of the parameters of your model just to match what is observed in COVID, WMAP, and Planck. So this is just, you fix one parameter, just setting the amplitude of the primordial spectrum to this value, and then get the predictions to characterize the whole spectrum that you observe in the CMB. That then this is given by the spectral index, how this spectrum just varies with the scale, and also the same that you produce this scalar, because at the end of the day, the fluctuation in the temperature are scalar fluctuations. You always have also tensor fluctuations, where are perturbing the metric. The field will perturb the metric, and we have the scalar component that will transmit directly into the temperature, and also directly the fluctuation of the metric, that are the tensor perturbation, that are the gravitational wave. Are just the own perturbation of the space time. So we have also in inflation just a prediction for some primordial gravity waves that are called the tensor, and then we compare with the observations. So let us see the observations, and I think that maybe we can stop for 5 minutes, and then we can continue. This is just how we make the main predictions. So we just characterize our model, and we get our amplitude for the primordial spectrum, and we get what is the spectral index just to characterize this spectrum, and we get what is the amount of primordial gravity waves that we can have in our model. See that everything is controlled by the Hubble parameter at the time of inflation, and just by the dynamics of the scalar field. What then we need to compare with the data. This is the latest data by the Plan satellite, and again, this is what inflation does for us. We need to get the spectrum just to explain this data, and what inflation does is just giving the initial conditions. The initial conditions, once we generate the spectrum, they go outside the horizon, they re-enter the horizon, and then we follow just with the standard evolution in our Freeman-Robertson-Walker metric, those perturbations. So inflation only set the initial condition just to generate the spectrum, and then we just plotted here the spectrum of the temperature fluctuations. This is versus multiple. The smallest multiple correspond to the largest scale, observable largest scale, and the largest multiple just to match a smaller scale. So this is what we need to do. And here, this is the data from the first relay of the plan data. And anyway, the red points, red dots are just the observation, and the solid curve is just the theoretical prediction. So there is a very good agreement between the way that we can describe the evolution of our universe and the data from the CMB. This is the latest data that just start just to constrain really what are the characteristics of our primordial spectrum, the initial condition just to generate this picture. And the big thing is that we haven't seen the primordial gravity waves, at least not on those scales, the scales that are available in the CMB. This is the big thing today, because at the end of the day, what we can see is only a reduced part of the spectrum that we generate during inflation. In terms of number of defaults, what we observe in the data for the CMB is just 10 defaults of inflation. And inflation must last like 60 defaults of inflation. So there are minimum another 40 defaults of inflations that are not accessible in the data from the CMB. And nowadays, this is what we want to see. If we can extract more information from those 40 faults and what is happening later, and where we can observe that part of inflation. To characterize this picture, all the information that we get is also the matter content of our universe that I mentioned before. So really, just to generate the spectrum, we only need to set 6 parameters: the characteristic of our initial condition, the primordial spectrum, and what is the matter content, energy matter content of our universe, and then the optical, another parameter related to the physics of the photons. And we know that today matter is roughly 30%, and then the other component that behave like a cosmological constant, and just to fit the data, this is the only thing that we need to assume, is roughly a 70% of the total matter content. And to explain that is also today a problem. If we compare just what we need to characterize the primordial spectrum, so we plotted this way. just the spectral index versus the amount of primordial gravity waves that we could have seen in the spectrum and that we haven't. So we just set limits to these primordial tensors, and these are more and more restrictive. Maybe in the future we will be able to see them, but today we know that this amount of primordial tensor must be less than 10% of the total spectrum. There is no evidence for any departure or the adiabatic, so one component, Gaussian scale, almost scale invariant spectrum. And this is, for me, is a pity because there is no evidence for, well, what is called isocurvature modes that could be related to the presence of other fields during inflation, non-Gaussianity in the spectrum. You only need a Gaussian spectrum and that's it. And then you can generate your prediction. That is also a pity because there are no evidence about the interaction of the inflaton field with other fields or the particle physics models that is driving inflation, or the running variation of the spectral index that are also related to the interactions. So at the end of the day, there is not much information about what is the potential that we need to explain this accelerated period of the expansion in the universe. So I don't know, but maybe we can stop here for 5 minutes and then we continue it, or
Yes, I think so.
okay.
May I have a question?
Yes,
May I have yeah, Munib, I'm Munib, okay, so you remember me, right? From
yes.
The first thing is, I think the dark age is now really reduced by a factor of 2. It's about 200 million, according to the radio observation of the Australian group.
Okay, yeah.
And this is somehow is funny. I mean, it's not clear why the canonical value was always 400 million. So it's just reduced by this observation. And it's not clear what really the reason is to be shorter than this. This will, of course, influence the condition, the initial condition for the star forming after the period of the dark age.
Yeah.
This is one thing I want to mention to you. This is Baumann et al. In Nature, this paper. And the other question I want to ask you, are you going to talk about the supermassive black holes later?
Not supermassive, because
no, okay, fine. But then the point is, do you have an idea that because we are with my PhD student, we are trying to look at the formation of the primordial stars, and this formation is affected by the magnetic field, the so-called cosmic magnetic field. Is that field could have been produced during the inflation?
This is a very good question. I mean, I'm not going to mention that because on all the things that are just a question mark, I forgot about that. This is still an open issue. I mean, how to generate the primordial magnetic field. And it's not close. I don't think that there are some mechanisms. You need to amplify your magnetic field. You need some dynamo effect. It can be during inflation, but I haven't seen any. I mean, at the end of the day, either you have to fine tune your model or you don't get enough. It is a very open question. Indeed, I also wanted to look at that with a student just to refresh myself what I knew from some years ago.
Yeah, there is this mechanism of the Biermann battery, but the Biermann battery came later eventually. So the seed field is an open question, and this is
No, no, what I mean is just also, I mean, the initial condition, the seed, and this is what I mean. And this is an open question that 8,000 years ago, that maybe what may happen immediately after inflation could be a good mechanism just to generate the primordial magnetic field, the seed of this, but
so okay, then we can play around with it because it's not clear.
It's not clear at all. I mean, the science is saying that the seed for the
that's an open research field.
Yes. Exactly.
Okay, thank you, Bob. Thank you for the talk. Thank you.
So if anyone, any of the students have any question, just what I cannot check is the chat. So I don't know.
In the chat, we don't have any questions.
Okay.
For now, yeah.
So maybe we can continue. I don't know.
Yeah, I guess you can.
Okay. So this period of accelerated expansion just allow us just to get the prediction for the primordial spectrum, just to generate this the spectrum of the CMB. And the important thing is that in this spectrum, the only thing that we observe is just 10 folds of the inflationary evolution. And we know that we must end inflation because we need to recover the standard evolution of our universe, starting with a radiation-dominated universe, and we need to recreate all the particles of the standard model. So that period, that bridge between the end of the inflation and the start of the standard radiation epoch is what is called reheating. How we transfer the energy density of our inflaton field that was dominating the expansion rate during inflation into just a bath of relativistic particles. Typically, the inflationary potential will have a region where we inflate, and then another one where the field starts oscillating around the minimum, and then it must couple to other particles because it must decay into other particles. It must just transfer the energy density into the radiation bath. And this period of reheating is the one that is important just to finally set how many folds of inflation we need. Because what we need is just to observe today. So this would be the moving wave number, and we need minimum that the largest observable scale today has been outside the universe during inflation. So when we propagate this relation, there is a part that depends directly on the inflationary period. There is some, then we need to follow the evolution of our scale during the reheating period. And then during the standard cosmological evolution, radiation and matter, or matter plus dark energy, that typically is, doesn't introduce any correction. So because of that, this famous number between 50 and 60 folds, and also depending on the final reheating temperature, that is the temperature at which the standard radiation epoch will start. This is what is called the reheating temperature. So our potential must include just a description of all this period. The region where we generate the primordial spectrum, the one to end inflation, because inflation must end, and then the one just to model this reheating period where we go from inflation to radiation. And this is a matter of modeling. We can just look into particle physics models just to see which description would be consistent with all the physics of inflation and the CMB, and still we discovered that we have more than 100 models. So the problem is that we don't have any other information either from particle physics, because we haven't seen any departure from the standard model of particle physics in the accelerators. And as I said, just the physics that describe the CMB is just very simple. It's just a Gaussian, practically scale invariant spectrum, and there is no indication of beyond the standard model physics. Some models are excluded, but in the moment that the data just excluded a model, then we discover how to rescue that model. And typically the simplest model of inflation, that is just scalar field with some polynomial interactions, in the simpler version, they are excluded because they tend to give too many gravity waves. I mean, a tensor to scalar ratio that is too large, and that today we know that the tensors are not there to certain level in the CMB. But we can always include the modification to this potential and just rescue this parameter. The important thing is that the tensor to scalar ratio, the limits on the tensor to scalar ratio, what is telling us is that the scale of the inflation must be lower than we thought at the beginning. So in a sense, this is what we need to do. We need to deform our potentials just to get the some regions at a lower potential energy where we can inflate. Other very interesting model is just, okay, the inflaton field is a scalar field, and the only fundamental scalar field that we can see in the accelerator is the Higgs. At least we know that there is one. So there may be another, but at least we know that we have the Higgs. So immediately people start just trying to set the potential just to describe with this Higgs field both at lower energy, the electroweak phase transition, at higher energy, higher values of the fields, a period of inflation. We cannot do it as such. We need to introduce a coupling between the scalar field and the curvature of our space-time, the curvature scalar. So we need, in some sense, just to go to some extension of our cosmological models. But in principle, this could work. It's just a nice model that fits perfectly well the observations. And the important thing is that by default, we have ensured the reheating period, because the Higgs will happen to all of the particles in the standard model. So at the end of inflation, the Higgs will decay and we will recover our standard model. So from that point of view, it's a very nice model. But what else? I mean, we cannot get more information about our particle physics model or the inflationary physics or whatever period of accelerated expansion is explaining us this giving the solution to the horizon problem. So maybe we need to look to other ranges of frequencies. And nowadays we know that we have finally just the evidence of the gravitational waves and that we can detect the gravitational waves. So far, we have seen just the gravitational waves coming from the collision of very compact astrophysical objects. But okay, so here is just different sources of gravitational wave depending on the frequency. Those corresponding to the CMB observations are here. They are very small frequencies, and those just are accessible to the terrestrial detectors, LIGO and Virgo are here. And then in the middle, just the future going to the space, and just the pulsar timing arrays and so on and so forth. And here is just similar cartoon, just frequency, CMB observation out of sight, and this cartoon, and the kind of amplitude of the characteristic spectrum for the gravity waves that depending on the sources and which are the experiments that may detect them. And this ELISA, ELISA is approved, and in some years to come, it will be put in the space. Then DESIGO and Big Bang Observatory, DESIGO, I think, I'm not that sure. But in principle, for example, these detectors were designed just with the hope of observing the primordial tensors, but at larger frequency. And it's not clear and we will be able, but as I say, what we generate during inflation will cover the whole range of frequencies. And the thing is that it depends. Those frequencies go outside the universe and then re-enter in the universe. And this cartoon is just comparing that, the physical scale. So this is the co-moving scale. So it goes outside and then it re-enters. The frequency at which we will observe today those fluctuations depends on when they re-enter. If they re-enter during reheating, that we can model by a matter period, or they re-enter later during radiation. The amplitude of these primordial waves, and they are here, is just the fluctuations, computing the spectrum of the fluctuations of the tensor fluctuation of the metric, how this amplitude behaves once they re-enter. In the universe, it depends on the epoch at which they re-enter. So they are suppressed during matter domination, and they are constant during radiation, because we compare the gravity wave behave as radiation and the parameter, and the density parameter is just comparing with radiation, so they stay constant. So this is the typical cartoon. If they re-enter during reheating, during matter, then the amplitude will increase during radiation. And today, that's the problem, is that today we need to set this to the level of what we observe in the CMB, that we haven't observed yet anything. But okay, this is just some years ago old paper. But then this is the prospect that maybe there is some hope that we could observe these primordial tensors in this frequency range, and corresponding to the primordial tensors that are just entering at the end of the reheating period, depending on what is the temperature of our reheating period. So there is the hope that maybe we could observe something in the future about the primordial tensor, just looking at another range of frequency, larger frequencies. But this is just the expectation, assuming that reheating, we can model it by an oscillating field that behaves like matter on average. But we can do many things during reheating. We need to model that period, and many things may happen. And maybe during reheating, what we have is not matter, not radiation, but something with an equation of the state that is just larger than radiation. So a stiff period and the energy density suddenly decreasing. And this will enhance our prediction for the amplitude of the gravity waves, because the fluctuation, the tensor perturbation just entering during that period will just suffer a sudden enhancement and just increase the amplitude. And okay, if we can see in this frequency range and some stochastic background of gravity waves, then maybe they come directly from the primordial tensors generated during inflation. So we need, so it could be some explanation, and if we can identify the signal, maybe that could tell us something about the reheating period and something about the inflationary models just behind and previous to that reheating period. Many other sources. I mean, this is what we are trying, given that we haven't seen the primordial tensors at the CMB scales in that range, is very small range of the frequencies, then we are looking now that we know that we can detect the gravity waves, then we are looking at some all possible cosmological sources of primordial gravity waves. And gravity waves are produced by many mechanisms. During the phase transition, just due to bubble nucleation, if at the end of the phase transition we have just a network of topological defects like cosmic strings, they will also radiate energy in the form of gravity waves. Or during reheating, there are other enhancement effects due to parametric resonance effect with the inflaton due to the coupling of the inflaton with other fields that can also enhance the spectrum, only that the frequency range is just even outside whatever planned future detector that we have, and it's just of the order of 1,000 on the megahertz range. And also they study, non-standard cosmology that can also give their own signatures for the gravity wave. So in this whole range of frequency that we hope just to have the gravity wave detector and the future gravity wave detectors, then we hope to see some signal of cosmological origin that could give us more information about what was happening previous to Big Bang nucleosynthesis. This is just the plot due to the prediction for different models of cosmic string. I don't know if you can see it, but okay. The solid lines are just the typical characteristic spectrum that one could expect from this model, and then the shade areas is just what could be seen by the future experiments like LISA. So everyone is expecting if we can see some new signal. And primordial black holes is just to comment a bit. Apart from the gravity from the primordial, I mean, primordial is just everything. It's something that is generated previous to Big Bang nucleosynthesis. But we have the spectrum of density fluctuation at the end of the day. This is what we generate during inflation. I mean, the scalar fluctuations just transfer to the curvature fluctuation of the metric, and this to the density perturbation of the our stress energy momentum tensor. But when we have some overdensities in this density spectrum of fluctuations, then on re-entry, we can generate primordial black holes. These are, as I say, just generated before Big Bang nucleosynthesis, and it's just, it may be originated just from the primordial fluctuations originated during inflation. They are not astrophysical black holes, so the others are just generated due to some other process, and later on during the period of structural formation. They are the black holes are just compact objects which radius is smaller than the Schwarzschild radius. So, and they will behave like their energy density when we sum the contribution of these black holes to the matter content. They behave like matter. So then they have been studying the possibility of explaining what is the dark matter content of our universe just with this kind of primordial black holes. They are a candidate for the dark matter of our universe. And there has been some discussion. I haven't followed it very clearly. I only want to mention these are light in the sense that their masses are just solar masses of the order of the solar mass or below. What we can generate due to these overdensities generated during inflation is just black holes that are with the masses below the solar mass. But there has been some discussion if it's LIGO, that is the one that is observing the collision of the gravity waves generated by the collision of the black holes, has already seen some evidence of these primordial black holes. Just, I only mentioned, but I haven't followed the discussion, so I really don't know if they are pushing too much the data or not. The interesting thing is that we can generate it during inflation, just twisting a bit the potential during inflation. We need to do something to our potential, but the thing is that if at the end we get some evidence of these primordial black holes, then we will get some more information about what can be the potential energy density during inflation. So this is just a characteristic, an example, a characteristic example of what we need to do. So this would be the potential, just some potential with is flat enough just to generate the perturbation that we see in the CMB, and then just some sudden transition, and then we continue the inflation in this region. So whenever we have this kind of sudden changes in the potentials, then what we do is that we amplify our primordial spectrum. So suddenly we amplify the perturbation. So at the end of the day, at the end of the inflations, if we just get the spectrum for the whole range of the frequency, this is in wave number in megaparsec inverse. What we will have here is just, okay, the almost scale invariant spectrum that we need to explain the CMB. So these tenfolds of inflation just cover a certain range of frequency, and in this range of frequency, the spectrum must be almost perfectly flat and scale invariant with a bit the departure given by the spectral index, and then we normalize the spectrum. And this, whatever, sudden transition here in this example, just a peak, just a saddle point, whatever, then give this enhancement are just some other much smaller scales corresponding to larger frequency, and this peak can reach almost 1. I mean, we are working, I didn't say, but we are working in linear perturbation theory, because what we need to explain is this temperature fluctuation of order 10 to the minus 5. 10 to the minus 5 is a small number, so enough with linear perturbation theory, and we don't need to go beyond that. But if we get the amplitude of the spectrum to be almost 10 to the minus 2 or 10 to the minus 1 on re-entering, this will imply immediately some overdensities on or smaller scales, and just by gravitational collapse, we will form the primordial black holes. So depends where we put this modification to our potential, this sudden transition or saddle point, or whatever we do with our potential, this peak in the spectrum at a smaller scale will correspond to some range of masses or another. And at the beginning, some years ago, when they also proposed that the primordial black holes could explain the dark matter content of our universe, there were some observations that say that, okay, there was no enough space because they couldn't account for the 100% content of the dark matter. But nowadays, it seems that some windows are open, and depending on the model, and these are just 2 examples, either double inflation with primordial black holes of the order of 10 to the 20 grams, or some Higgs inflation. Indeed, it is fine-tuned. I mean, when I say Higgs inflation, you need to fine-tune your parameters in the potential just to get the peak, and enough inflation not explain everything, but it's possible. And also Higgs inflation is the one that naturally will give us just the reheating period and will generate the standard model. So still, it's a very nice possibility. And we can also generate a peak that accounts just almost for the total dark matter content of our universe. So this is the kind of things that in inflationary physics they are studying today. Beyond the frequency range that we can see in the CMB, given that has been a bit disappointing, because just a Gaussian spectrum with just an amplitude, almost a scale invariant, no signature of non-Gaussianities or whatever, will explain the data. So we are moving and we are trying to see, okay, where we can see the other frequencies that we also generate during inflations that re-enter after inflation has ended, and maybe during reheating, maybe during radiation, maybe during the first times of the matter domination period, and what kind of signatures we can have for this period. So at the end of the day, just the summary is a very incomplete list of open questions in cosmology and also particle physics. This is really related to both. And before, what I had talked is always before Big Bang nucleosynthesis. By today, we cannot explain really what is the nature of the matter content of our universe. What is the dark matter? What is the dark energy? This is a big question mark. And the radiation, yes, this is what the only component that we really know and we can describe very well. And because some standard problems that we need to explain, the flatness problem, the horizon problem, that is for me the important one, cosmologists propose a period of accelerated expansion that is called inflation. Now, we need to we need to explain what is the potential that drives inflation, and we need to look for signature of the physics of inflation. In the CMB, we haven't seen much. We can explain it, but there is no much more information. So we are looking just to some other regions and trying also to link the inflationary physics with the dark matter problem that may be in the form of primordial black holes, to characterize really what is the signal of primordial gravitational waves that we can generate during inflation, and if there will be any hope in the future with the future detectors of observing those signatures. So that's all. This is what I was planning to describe.
Thank you, Mar, for this very
comprehensive
lecture. It is without a long break. We'll listen you with very excitement. I think Munif want to say something.
I have a very good question. I have problem with this black holes. Okay, actually, you are saying you have some three categories of black holes. Okay, so the primordial black holes. I mean, I understand that if we form very massive stars later after dark age, we can get what you call stellar black hole is not the right description. These are black holes at least more than 250 solar masses. These coming from non-successful supernovae. But then this primordial black hole is dark matter black hole. When we form the stars, the first stars after dark age, we have the so-called lambda CDM model, which is at 1 million solar mass of dark matter in which the star is formed, or many stars are formed. So what are these primordial black holes?
The primordial, what I was meaning, because obviously, I mean, because of that, I was saying that I'm not an expert on the, I don't know much. I mean, you are the one that can tell me much more about those other black holes. What I refer to the notion of the primordial in our community is whatever that is originated before Big Bang nucleosynthesis and physics, before Big Bang nucleosynthesis, and that indeed today is thought that is related to the inflationary physics. So it's just some regions of the universe. So what we have is that the fluctuation originated during inflation will re-enter the horizons. So when they re-enter the horizon is what we can just apply our evolution of the universe and just see what is happening to those fluctuations. So the thing is that if these fluctuations are very large, almost the amplitude of those fluctuations is just the curvature fluctuation or the energy, the density fluctuation, and almost one, they will immediately create some very overdense regions that will collapse. I mean, the concentration of energy density is so large in that region of the space that they will gravitationally collapse and just form black holes. And this is what I understood as primordial black holes. And the mass of those primordial black holes depends on the characteristic frequency at which is located the peak of the spectrum. And typically what you get is just masses of primordial black holes that are smaller than the sun mass. So this is what this is just the description coming from the inflationary physics. So it can give you a population of just very small black holes. Depending on the mass, I mean, I had only just including the samples for those that can account for the dark matter today. But during it, the fluctuation that are just growing are just those that are just re-entering during reheating. What you may generate is very, very light primordial black holes that immediately evaporate. So not all of the primordial black holes eventually that you can generate due to the inflationary physics will survive until today. Because of that, I say that, okay, you need we wanted with inflation, we wanted to escape the problem and to avoid the problem of having to fine tune things in cosmology. And some years later, some decades later, what we are doing is just fine tuning the parameters in our potential just to get some prediction. So this is really fine tuned. But it's just because of that, of some overdensities that are created immediately when the fluctuation re-enter the horizon. So you have a very overdense region that collapse. Spherically collapse, and they discuss a lot about the details of all this. But
Hi, Mar.
hi.
Can you hear me? Okay.
Yes.
So related to this subject, I remember a couple of papers by Jeremy Ostreicher and co-worker about this. I think that they were the first to propose the deformations in an inflationary scenario of these primordial black holes. But one of the arguments they claim in favor is not only the possibility that this primordial black hole may explain at least part of the dark matter, but also because they can explain, since they form very, very early, in the universe, they have time to accrete to the mass of the supermassive black hole that are observed in a very early epoch, AGN and quasar are observed at very high redshift. So I remember this paper that I think are interesting, this point of view. And the other things, but then I have a questions about the possibility to observe in the future, not now, of course, not with the present detector, but the cosmic neutrino background, that we expect to be there. And the question is, eventually, what we can learn from an observation of the cosmic neutrino background that we don't know already from the CMB, for instance. So we know that there should be cooler, no? The neutrinos should be cooler than the radiations. So in principle, the difference in the temperature may tell something about the entropy of the universe before the BBN. But I don't know. So my question is what we can learn from an observation of cosmic neutrinos.
That's a good question. And about the primordial black holes, I fully agree. I mean, I was only stressing on the one of the aspects, because the other for me is just yes. But it depends on the population of primordial black holes that you may be able to form, and they are discussing and the consequences for the structure formation and just being the seed for the supermassive black holes, indeed. But and about the the cosmic neutrino background, very good question. At the end of the day, is we know that then they decouple around 1 MeV. So yes. Before Big Bang nucleosynthesis. So we like whatever we can learn about before Big Bang nucleosynthesis may help. And the one thing, okay, and what for? Because, okay, we already know that they are colder. So what we are going to learn? Well, it's just about the effective number of degrees of freedoms that were present at the time, even from nucleosynthesis, bring back nucleosynthesis, and this is what then they really constrain. And constraining this number really constrain the kind of beyond the standard model physics that we can input just to explain the cosmological observation. So maybe there will be some surprise. Maybe we will learn something just because of that, just really being able just to measure that small difference this small difference is directly related to whatever was there just right before Big Bang nucleosynthesis. I'm not that optimistic, but okay. I mean, there has been always many surprises in cosmology, so I don't know.
Perhaps next generation of cosmology will see it.
Yes. I think that interesting thing will come from other sources, not really from measuring, but maybe. Or maybe we will discover that it doesn't fit really what we thought that it will be happening, and we will learn a lot about. Also, because we need to set it's related also to the neutrino physics. We need to really. We still don't know. We know the mass differences, but we don't know the masses of our neutrinos. So. It will be related to neutrino physics. It will be able just to learn in first from cosmology or from particle physics experiments. We don't know, but maybe cosmology will tell us about the neutrino masses if we are able just to measure that cosmic neutrino background.
But no, sorry, I'm thinking about. I'm very ignorant about that, but the fluctuation, the temperature fluctuation are very primordial, no? Come from the inflection, as you have shown.
Yes.
But the fact that the neutrino decoupling occurs so early, in principle, this fluctuation.
I'm losing you, Oscar.
Oscar, can you repeat your question, please? The last part we couldn't get.
Okay, no, the point is that since the neutrino decoupling occur very early, the temperature fluctuations should be more clean, I think should bring a more clear information about the original fluctuations from inflection. I mean, with respect to the fluctuation that we observe in the CMB, that maybe they could be perturbated later. I don't know.
Maybe I was thinking that we still need to fix the physics, the neutrino physics, just to get there. So I was more maybe, but okay. So it's just that we had different concept of early. For me, one MEV is not that early. Sorry, but yes, it's true.
Thanks.
So that at the end of the day, you have to evolve. Yes, but if you have to evolve then your fluctuation, you only need to do it until that epoch. But I think that the problem with the neutrinos is that you need first to really know your neutrino physics, just to start. And the first information will be about the neutrino physics, but maybe you're right. It's only that in my concept of scales, that was not that early for me.
Are there any other questions for Mark? If not, thank you very much. Gracias, muchas.
Gracias.
Gracias.
Thank you.
Thank you. So now we have a short break, like 20 minutes before Maria Rosa. So in 27 minutes, let's say in half an hour, we can meet again. So,
Sinan, maybe Maria Rosa would like to test if she can share the presentation.
Sure. I am here. Yeah,
okay.
Maria Rosa, if you want to test, if you like.
Okay, sure. So shall I try it right now?
Yes.
Perfect.
Hi, Maria Rosa. Hola.
Hello everybody.
Hola, buenos días.
Buenos días. So is it okay?
Yeah, we see perfectly. If you do play.
So I start the presentation.
Perfect. Thank you.
And it moves. Perfect.
Okay, so we have time for a coffee.
Yeah, we have time for a coffee break.
Okay, so I stop the presentation.
Yeah.
Okay.
Yeah, we can do that.
Perfect.
Perfect.
So enjoy your coffee.
Okay, hasta pronto.
Hasta pronto.
Muy bien, Sinan. Hasta pronto.